Hi, can everyone hear me? Okay, that's good. How was everyone test? Do you find it easy? Yes. I feel like most of the questions were covered in the lecture or tutorials already. The one that students struggle with the most probably was the fourth question. You need to consider cases for that one. Okay, let me share my screen. Oh, the 4721 question. Yep, that question. Like students were kind of confused about that. My feeling is you have trouble figuring out what cases you have to include. What do you talk about in the lecture today? Did you go over combinatorial arguments as well? I saw professor include this one in like the reading for the lecture today. So I also included the problem about this. Hopefully that you went over it a little bit in the class. It's not really something new. I think it's what you learned already. So first we will talk about combination. If we recall, last time we talked about permutation, and we also talked about permutation of multiset. Let's say you have a set S contained n elements. They might be distinct, but they don't have to be. And you have like k categories in the set S, like type 1, you have n1 objects. Type 2, you have n2 objects. Up to type k, you have nk objects. And you also have n1 plus n2 plus up to nk is equal to n, because we know that our set S contains of n elements, and we kind of partition them into different types. Type 1 has n1 element, type 2 has n2 element, type 3 has n3 element, and like that until type K. And if you add the cardinality of each subset here together, you will get the cardinality of the whole big set, which is n. And we say that the number of ways to arrange all elements in X is n factorial divided by n1 factorial, n2 factorial, up to nk factorial. So we were talking about this one. And how does this relate to combination? Let's say I have 3 objects, A, B, C, and I want to choose 2 objects out of the 3 objects here. Then I can choose AB, AC, or BA, right? But the combination means that the order doesn't matter. So if you get AB or you get BA, we call it is the same because we have the same combination. It just means the order doesn't matter. So one way you can count the number of ways to choose 2 elements out of 3 like this is by the notation 3 choose 2. It denotes the number of ways that you can choose 2 elements out of 3, where the order doesn't matter. Or another way you can look at this problem is that since you have 3 elements and you want to choose 2, then you can think of as assigning label. N stand for chosen. Since we want to choose 2 elements, we can think that we have 2 labels chosen, and N stand for not chosen. Then the process of choosing 2 elements from these 3 is the same process of assigning these labels to the 3 here. For example, if you assign A chosen and assign B chosen, assign C not chosen, then it is the same as we have the group AB. How about AC? AC is when we assign chosen to A and chosen to C and not chosen to B. BA is the same as AB, where we assign chosen to A and B and not chosen to C. So the number of ways that you can choose 2 elements out of 3 like this is the same number of ways that you can arrange the word C, C, N. And this one is just permutation of multi-set, where you have 2 types. Type 1 is C, you have 2C. Type 2 is N, where you have 1 N. Then the number of ways that you can arrange them is 3 factorial divided by number of elements from type 1, number of elements from type 2. And it is equal to 3 choose 2. Does this make sense? This is why you have the formula for the combination of N choose K. In general, you will have N choose K is equal to N factorial divided by K factorial times N minus K factorial. This is because you can think of the process choosing as assigning labels chosen and not chosen. So after you choose something, it creates 2 groups. The first group is the group that got chosen. The second group is a group that get not chosen. And then within each group, the order doesn't matter. So that's why you have these 2 numbers in the denominator. Please stop me if at any point you feel like what I'm saying just don't make sense, because it's important. Another property that you might see is N choose K equal to N choose N minus K. Algebraically, this should make sense because N choose K is N factorial divided by K factorial times N minus K factorial. And the right-hand side is N factorial divided by N minus K factorial and N minus K factorial. I'm applying this formula to this one. And if we simplify it, we will have n minus k factorial in the denominator. And this term, n minus n, cancel each other out. So we are left with k. So since these two numbers are equal, so n choose k is equal to n choose n minus k. That's how you show it algebraically. But you can also show it in the more intuitive way, which we call combinatorial argument. Let's say I have 5 balls. And I want to count the number of ways that I can choose 2 balls out of these 5. I want to choose 2 out of 5. Let's say I want to choose 2 balls out of the 5 ball to give to my friend. Then you can see that I can choose this ball and this ball to give to my friend. Or I can choose this one and this one to give to my friend. So in general, we say that we have 5 two ways to choose 2 out of 5. However, the process that you choose 2 balls out of 5 to give to your friend is the same process as you're choosing 3 balls to not giving it to your friend. So those 2 actions are equivalent. Does this part make sense? Yes. Let's say these balls are distinct. Like, let's say I choose B1 and B2 to give to my friend. It is the same thing as saying I choose B3, B4, and B5 to not giving to my friend, like just to throw away. So these 2 processes are equivalent. Therefore, the number of ways to choose 2 out of 5 to give to your friend is the same as choosing 3 out of 5 to not give it to your friend. And then we can generalize it. Let's say now you have n balls. And you want to choose n minus k balls to give to your friend. Let's say you choose these k balls to give to your friend. Then what is it equivalent to? It is equivalent to you choose the remaining, which is n minus k. You choose the remaining balls to not give to your friend. So that's why these 2 expressions are equivalent. Please make sure that you understand all the thing I'm talking here is really basic combinatorial arguments. The questions that we deal with later will be more complicated. So I will want to make sure you have a good foundation of this. So you can see here that for combinatorial arguments is pretty intuitive and it does not involve any algebraic manipulation or like calculation at all. It is just 2 ways to count the same event. If there is no question, I will give you maybe 5 minutes to solve this one. You will see that part 1 we covered in the previous tutorial, but because now we talk about combination, it makes sense for us to solve question 2. So that's why I put it in. I will take this up at 2:30. Please let me know if you have any question. If you don't understand what's the question asking, you can send me private message. Does order matter for 1? It does, because the gifts are distinct. Like if you give friend 1, gift 1 and gift 2 is different from that giving friend 1, gift 3 and gift 4, right? Because the gifts are distinct. Even though in this case, friend 1 received 2 gifts, in this case, friend 1 also received 2 gifts, but they are different because the gifts themselves are different. But for part 2, these 2 are the same because all the gifts are the same. So now you just care about how many gifts each friend gonna receive. For part 2, I recommend you to think of this configuration. This one means that friend 1 received 3 gifts, friend 2 received 3 gifts, and friend 3 received 4 gifts. So if you place these 2 vertical lines somewhere else, let's say I don't put it here anymore and I put it somewhere like here, then it give me different distribution. This distribution will be correspond to friend 1 receive 1 gift, friend 3 received 1 gift, and friend 2 received 8 gifts. Yeah, so think about that. Okay, it's 2:31, so I will take this up. For the first question, how many distribution are possible where we have 10 distinct gifts and we are not being restricted by how many gifts each friend has to take? So we can think of as we have 10 gifts, give 1, give 2, up until give 10. And we will decide. The first step is decide how many possible choices are there. I can give gift 1, 2. I have 3 friends, right? So I can give gift 1 to friend 1, friend 2, or friend 3. So I will have 3 choices. I will look at that answer later. And then I will decide who I can give gift to. I have 3 choices again. I can just give to any of them, friend 1, friend 2, or friend 3. And I do like that until gift 10. And I would have 3 to the power of 10 distributions are possible. Let's see, I see another student answer permutation. That would be true if you think of like each friend just received 1 gift, then that answer will be true. But here we want to distribute all the 10 gifts to the friend. Move on to the second question. Now the gifts are identical. So whether you give friend 1, like give 1, give 2, give friend 2, give 3, give 4. Now it is the same as giving friend 1, give 3, give 4, and friend 2, give 1, give 2. Why is that? Because now all the gifts are identical. You will just write them as G instead of assigning any specific label. So you have friend 1 having 2 gifts, friend 2 having 2 gifts. So it would be the same as friend 1 having gift 3, gift 4. Now I just write as gift. So is again 2 gift, and friend 2 also 2 gift. So what is the criteria that differentiate between different distribution? So you can tell that 2 distribution are different if the number of gifts that each friend receives are different. For example, you give friend 1 1 gift, friend 2 1 gift, and friend 3 8 gift. This distribution is different from giving friend 1 2 gift, friend 2 2 gift, and friend 3 6 gift. So it boils down to how many gifts that each friend receives. So I can use the configuration here. So this one is saying that friend 1 received 3 gifts, friend 2 received 3 gifts, and friend 3 received 4 gifts. If I move the vertical line to somewhere like this, this configuration means that friend 1 received 0 gift, friend 2 received 6 gift, and friend 3 received 4 gifts, which means the number of ways that you can distribute the gift if the gifts are identical is the same problem as how many ways are there you can arrange this sequence of characters. And this sequence of character, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 characters. Out of them, you have 10 letter G and 2 vertical lines. So the number of ways to arrange them is 12 factorial divided by 10 factorial times 2 factorial is permutation of multiset. And another way you can think of it is that now you have 12 spots. You have 12 spots in total. And you can choose 2 spots out of the 12 spots to put the vertical bars in. Because once you decide the position for 2 vertical lines, the remaining spot will automatically belong to the G letter, and it will give you one distribution. So this one would be the final answer. Any question about this one? You will need to use this kind of argument when you are having like some identical objects and you want to distribute them into some like placeholder. Like here, I think a friend 1 as 1 placeholder, friend 2 as 1 placeholder, friend 3 as 1 placeholder. And then all the objects that I'm trying to fit in each placeholder are identical. So that's why you should use this formula. Another typical problem that you might see will need to use this kind of argument is find all like find number of non-negative solutions to something. You will have some equation there. For example, like x1 plus x2 plus x3 equal to 5, something like that. So this is another common question that you might face using this kind of argument. If there is no question, I will let you attempt question 2, maybe 3 minutes. If you are still confused about question 1, please let me know. Okay, let's look at question 1. Here, you have a class of 30 students and you want to form a team of 11 members and another team of 5 members. And I want to count how many ways are there. I can form 2 teams like that, such that nobody can be on 2 teams. So step 1, I can choose member for the soccer team. I have 30 students and I need 11 members. So out of those 30 students, I can choose 11 students. So I have 30 choose 11 ways to complete step 1. And step 2 is choose the member for basketball team. I want to make sure that nobody can be on 2 teams. So whoever got picked for the first team will not be eligible to be like picked for the second team, which means I have to exclude those 11 members that got picked in step 1. So I have 30 minus 11, which give me 19, because only 19 students are left after I complete step 1. And out of those 19 students, I will choose 5 students to be the member for basketball. I have 19 choose 5 ways to complete step 2. And then I can multiply them together. 30 choose 11, multiply with 19 choose 5 ways to form 2 teams such that nobody can be on both of the teams. Does part 1 make sense? Is 30 choose 5, 25 choose 11 the same thing? Yes, yes. So you can also do another way is first choosing a member for basketball team, which give you 13 choose 5. And then after that, you choose member for the soccer team, which give you 25 choose 11. They should give you the same answer. If there's no question, I will move on to part 2. I allow any number of students can be on both teams. So again, first I choose the member for soccer team, 30 choose 11. And step 2, now I don't have restriction like part 1. So out of the original 30 student, I can choose any 5 students to be on the basketball team as well. So this would be my answer for 2. For 3, I want at most 1 student can be on both teams. At most 1 is less than or equal to 1. And we know that the number of students can be on both teams. Minimum is 0, right? Minimum is 0 students are on both teams because the number of students cannot be negative. So I know that it is at least 0 and at most 1. So it should be 0 or 1. I see a student answer here, which is 30 choose 11, and then 19 choose 5, plus 30 choose 11, and 20 choose 5. Yep. Let's see. So the first case here represents for nobody on 2 teams. And this one, I suppose you mean that exactly one student on two teams. But does it make sense? Does this mean that exactly one? Here you are picking 11 students from 30 to be on the soccer team. And then you say that, okay, I will have one student from there. I put back into the population. And then from that population, I will choose 5 members for the basketball. But does it guarantee that there will be someone from the soccer being included in those 5? If you do 20, choose 5. Is there guarantee that will be exactly one student from the soccer team also in basketball? The answer is no. You cannot guarantee that. Like, let's think about it. You have 30 people originally. It is 30. And let's say that you pick these 3 to be in soccer. Okay. And you want that exactly one student will be on both teams. So you say, okay, I will not subtract 3 when I choose the member for basketball, but instead I only subtract 2. Let's say I only subtract these 2 and I allow this one to be chosen to be in basketball. And then I do like, here is 28, choose 5 to be on basketball. The question is, can you guarantee that this person already in soccer, can you guarantee they will be picked to be in basketball? Because if not, then you also count the number of ways that nobody can be on 2 teams, right? So you overcounted. So what you should have done here, I will cross this out for now. What you should have done here is, I choose 11 members for the soccer team. Out of those 11 members, I choose 1 to be in basketball team. And out of those people that was not in soccer, I choose 4 people to be in basketball team. So this will give you the correct answer. So that is the first way. The second way is, you just let 30 choose 11, multiply with 20 choose 5. This itself would be sufficient to stand for both the case nobody on 2 team and exactly 1 student on 2 team. So you can do the addition like this or just a single expression like this. Any other question?
Could you explain the 30, 11, 11, 1, 19, 4 one more time?
This one?
Yeah.
Yes. So I was saying that this expression, it does not correspond to exactly 1 student on 2 teams. Why is that? Because first you pick 11 member to be included in soccer. And then you decide that you will allow 1 to be go back and being like, they have the possibility to be picked to be basketball. Just like this. First, you pick 3 people for the soccer team. and then you return 1 byte, and you pick 5 people out of those 28 to be in basketball, right? However, if you take 5 people from these 28, there is no guarantee that this one will be included in those 5. They might just pick the last 5 here, then this one will not be included. Which means in the case this one is not included, the 28 choose 5 here also allowed for none of the member are on both team. Because in that case, you will have soccer is these 3, and then the last 5 is in basketball.
Oh, okay,
Which
okay.
you actually over count because you already counted here. Does that make sense?
Yeah, I get it now.
Yep. And this one is just like choose 11 member for the soccer team. And out of those 11 member, I choose 1 to be on the basketball so that I will have exactly 1 student on both teams. And then the rest member of basketball, I chose from those students who haven't been picked for soccer. So if you add those 2 together, you will get the correct answer. Or a shorter way you can do is this expression here. If there is no question, I will move on to part 3, question 3. I will guide you through this one because I'm pretty sure it's a new concept. We want to give combinatorial. Would this work as well? I will look at that by the end of this session, just so we can at least cover question 3. Okay, I want combinatorial argument to show that this equality hold. I don't want to use any algebra. I don't want to like expand this into something like this. I don't want to expand like that. I want to show that the left-hand side is equal to the right-hand side because they are counting the same event. Okay. So the easier side to start with is the right-hand side because it's so intuitive to us. What is it counting? It's saying that I have 2 n elements and I want to form a group of n out of those 2 n elements. So let's say I have n black cat. Okay. I have n black cat here. And of course, all the cats are distinct. And then I have another n orange cat. The right-hand side, what is counting is how many ways are there. I can choose n cats out of all these black and orange cats. Okay, so my question, the question that I want to answer is how many ways are there? To choose n cats out of those n black cats and orange cats. So this is a question that I will answer. I will show you that the right-hand side is the answer to this question. And the left-hand side is also the answer to this question. Since they are both the answer to this question, they have to be equal. So that is my proof strategy. So I have n black cats and n orange cats, which means I have 2n cats in total. And I want to form n cats, which just means out of those 2n cats, I pick n cats. So that is the number of ways that I can choose n cats out of n black and n orange cats. Does this step make sense? Please stop me at any point you feel lost, because it's very easy for beginner to be confused by this kind of proof. Next, I will move on to, and the left side is choosing individual amount and squaring it because we need black and orange. Yeah, you kinda got the idea. But how do we do that specifically? So let's think about it. I want to choose n cat out of those black and orange. So what are the possible cases? The possible case is out of those n cat that I chose, there are 0 black cat. If there are 0 black cats, then I would need n orange cats, right? Or I can have 1 black cat. And if I have 1 black cat, then I only have n minus 1 orange cat. If I have n black cat, if I have 2 black cats, then I would need n minus 2 orange cats. Just like that, until the maximum number of black cat I can have is n. Because I'm trying to choose n cats out of these. So maximum, I can only have n black cat. And if I have n black cats, then I would have 0 orange cats. So those are mutually exclusive cases because they cannot happen together. Either it is this case, or it is this case, or it is this case, something like that. So every case are pairwise disjoint. So I will count how many ways are there that I can choose 0 black cat and n orange cat. So I will look at the number of black cat I have. Out of n black cat, I will choose 0 to be included. Out of n orange cat, I will choose n to be included. However, it is the same as out of n black cat, I choose 0 cat to be included. And out of those n orange cat, I choose 0 to be excluded. If I exclude 0 orange cat, it is the same as I include n orange cat. Similarly, for the next case, out of n black cat, I choose 1 to be included. Out of n orange cat, I choose n minus 1 to be included. And it is the same as out of n black, I choose 1 to include. Out of n orange, I choose 1 to exclude. I choose 2 black cat to be included, and I choose 2 orange cats to be excluded. Last step is I choose n black cat to be included, and I choose n orange cat to be excluded. And you will see here is n choose 0 square, n choose 1 square, n choose 2 square, n choose n square. So if you add them all together, you will have this. Which is the left-hand side. So you see that the left-hand side counts the number of ways to choose n cat out of those n black and orange cat as well. And this also counts this problem. Therefore, they have to be equal. And it will be the end of your proof. Any question about this one? Yes, you're expected to do this one on the exam. If you look at the past exam or the test, there was also question relating to combinatorial proof. If you don't like call it proof, you can say like combinatorial argument, if it sounds any better. This question was in the past test, I believe. You should attempt this on yourself. What I can give you hint is that you will want to partition based on the largest or smallest element of the subset. You will need time to think about this. If you got stuck, feel free to post on Piazza. There's another way, like there's so many ways for this kind of problem, so many solutions possible. Another one involve like counting the path from 0, 0 up to n. Like the path where you can only like go to the right or going up. We call it lattice path. And I believe you also cover this in lecture. It can give you another way to prove that the identity hold. If there is no question, is the end of our tutorial, and I will see you on Wednesday.